Hello everybody, I am Cariou from the University of Pau in France, and I'm going to present my paper called the software development process based on UML state machines. So to start this talk, a bit of history, the birth of the model-driven engineering field with the model-driven architecture of the object management group 20 years ago. The goal of this approach was to have a full model approach for software development. The main idea is to shift the complexity of software development from coding to modeling. And for that, UML-based model must embed a complete software specification, a complete application definition. And after, code generation can be used to generate the concrete application from a specific implementation technology. At this time, there are some limits anyway. First, it's UML, OCL, and MOF models were not sufficiently precise to define all the concrete part of an application. So typically, the technical or algorithmic parts of an application was difficult to define them in UML. So to fill this void, 10 years after, another specification from the OMG, fundamental UML, FUML. As expressed in the introduction of the document, FUML is an executable subset of standard UML to define in an operational style the structural and behavioral semantic of systems. Concretely, you can express FUML using specific activity diagrams or a textual syntax that is called ALF. So here, for instance, a basic example of FUML. On the bottom, you have the syntax, the graphical syntax under the form of a kind of activity diagram. And what is more interesting is on the top, you have the textual syntax of a FUML specification using the ALF syntax. So as you can see it really looks like a standard code. It's a definition of an operation with parameters, a return value, and some other call of other operations. So it looks like code, and concretely, thanks to FUML and other specification, now in UML models you can attach abstract code to elements of the models. So this code is abstract in the sense that it's not relying on a particular programming language, but it is like code because it's compilable towards some implementation platforms, and it is also interpretable in tools. The FUML specification is implemented in modeling tools such as Barbier, which is an Eclipse modeling framework based on the Eclipse modeling environment. However, this full model definition of an application raises some open questions. So the first question is, does it scale? So if I have to develop a very big application that in a classic way will require to write millions of lines of code, is it possible to make the complete specification of this big application at the model level with UML models and FUML specification? So it's not sure that currently the tools are able to manage such a big specification. The other question is, if I have existing libraries, I have legacy code, or if I want to use a specific IDE, how can I do? So, for instance, if I want to develop a mobile application, an Android application, I can use the Android Studio tool, but Android Studio is not Eclipse based, and it's not made to embed a UML or neither FUML specification. So it will be difficult to define in an abstract way with FUML and Android application if it's not possible to use it with Android Studio. So for all these reasons, we propose to still have a model-based software development process, but to have a more pragmatic approach and to have an intermediate approach between modeling and programming. So what we propose is to still have a part of the system that is defined by a model, including at runtime. And this model will be an executable model. Concretely here in the paper it's a UML state machine, but it can be any kind of executable model. So this model will be executed at runtime. It's interesting because it enables to, even at runtime, to have the specification of the behavior of the system at a high level of abstraction. The models that will be executed at runtime will be also the same as the ones that will be defined at design. And at design, it can be simulated, and that will enable to have an early detection of problems. So on one side, you have the behavior of the system defined by a model that is executable at runtime. And for the rest of the application, for all the technical part, managing the data persistence, the distribution, and the most important part for implementing the business operation, the business part of the application, so we propose to remain with the regular programming language. In the paper, we use Java for programming this business operation. So here, for instance, UML state machine that is specifying the behavior of a microwave oven. There are two main states, closed and open, based on the fact that the door of the microwave is open or closed. There are transitions associated between states, and this kind of state machine is executable in the sense of you can process events, and the processing of events makes the state machine evolving. For instance, here, the door open event occurs, the active state was baking, and we follow the transition from baking to pause associated with the door open event, and it leads to activate the paused state of the open composite state. So we have executed here and one execution step associated with the processing of an event. But concretely, if I embed this model at runtime, and if I am able to execute this model in my application, what concretely do my application? Currently, nothing, because what is missing and what is very important here to have is to make the relationship between the model that is executed and the business operations that are concretely managing the hardware, the microwave. So here, for instance, we have the heat method, that is a business operation, controlling the microwave to make it heating, and for that it puts the light of the microwave on, and it puts the magnetron of the it activates the magnetron of the microwave. So this business operation, what we need to do is to associate it with the elements of the state machine. For that, we propose to use our Power tools. So Power is first an API for programming UML state machine. You can define state, transition, and what is important, you can associate business operation with these elements. Here, for instance, I'm making the instantiation of a state called baking, and I am associating as an entry action the it method, that is the one that is defined here, that will be executed on this business object. That is the object that is implementing the it method. So thanks to that, I have defined a state, and I have associated with the state a business operation. And the second part of Power is an engine, execution engine, that will process events. So it will make evolving the state machine, it will change the active state, and during the change, it will execute the business operations associated with the state and the transition. So that's interesting because now we can program UML state machine and have the link with the business operation. But it's code, it's not model. So how can we do to start from model? So for that, we propose the following concrete development process. First, you start by defining your UML state machine using your favorite UML modeler. An important point when you are defining your state machine is to associate business operation with state and transition. So here, for instance, we retrieve the baking state, and as entry we have the it operation. So what we put here for the moment is only the signature of the business operation. So it's not the code, it's only the signature of the operation to say that the baking state is associated with an it business operation. This it business operation is besides implemented in plain Java. So the second step is to implement all the business parts, business operation of your system. So in regular Java, so it's not anywhere a model here, it's a full Java. Then we have developed a Power code generator. It's a web application that takes as input a UML model and generates the code of the equivalent UML model for the Power API. So here we have this code is generated, it defines the UML state machine of a microwave within the Power API. And for instance, here we retrieve the same line of code we have written by hand. So now this code has been automatically generated. It defines the baking state and define as an entry action the it method, because you have put in the UML model that the it operation is associated as an entry action with the baking state. So on one side you have the equivalent of the UML model in Java for the Power API, and on the other side the business operation. The link between the business operation is already made by the code generation, and you just have to execute with the Power engine the mix of the state machine code and the business operation, and you got your running application without almost any modification to make on the generating code or the business code. So as a conclusion, we will propose in this paper a pragmatic model software development process, an intermediate approach between programming and coding. On one side, we propose to model the behavior of the system with an executable UML state machine. What is interesting here is we can do a seamlessness development, because the UML state machine specified at design is exactly the same as the one that is executed in the running system. So thanks to the code compilation from UML model to our Power code, and the rest of the system is implemented in regular Java, the business part, technical business part and technical part. And after, there is direct association, as we have seen it, between the model and the business part. We have tried to be the most independent of the tool, so we have a web application for generating the code to Power, so you can use the UML tool you want to modelize, to specify the state machine, and you can also embed the Power Engine in any Java project, as it is a very light tool, and only 100 kilobytes jar file to be able to use the Power in any Java project. Thank you for your attention.